There you go. All to you.
Thank you so much, Bruno, and thank you for surviving to this last lecture. And today, let me start ask you if you have some questions about the last lesson. Yesterday, we did a review of many topics. Mainly, we studied the power spectrum in terms of the quantum treatment. Do you have any questions to start?
I just muted the person. Yeah, sorry about that.
Okay. Sorry, I thought it was a question. Okay, in that case, if you don't have questions, let me start talking about the questions that we asked yesterday. Yesterday, we compared the expression for the power spectrum in terms of the spectral characterization. I try to say the power spectrum wrote in terms of Fourier transformations. And we discussed yesterday that in that case, we trade with an average because the people considered an average over the possible, over different universes, but it's only an hypothetical situation which lets the possibility to deal with an average. But in practice, we know that we only have one universe. And with this universe, we can extract the data for the observations, but it's different in the situation in which the people consider an ensemble because they thought in an hypothetical situation. So someone is asking in the chat, can you remind me why the perturbations give information about the structure? Yes, for sure. Give me a second and I can show you how happened that. Let me use them, if I remember well, in the pre-session we studied. The power spectrum is related with the density fluctuations. Perturbations part, let me, maybe, I'm not sure if it's in this, no, I thought it's not this presentation, but we studied that the data that we can study from the CMB is right in terms of the temperature of the CMB. And also we studied that when we study the perturbations in the background, on the background, we can write the metric in terms of the Newtonian potential. Let me see, this is the no, sorry, this is not the, I try to find the right presentation here. I thought this is the presentation is the tree. Let me, sorry, but yes, I have the right presentation. Let me share with you this spectral characterization. Right, and let me read the question again. Can you remind me why the perturbation give information about the structure? The people try to study the perturbations on a background. And then we study that they write the metric with this form. So the background is homogeneous and isotropic. And then we try to describe the inhomogeneities and the anisotropics that the geometry have. And the people characterize using scalar perturbations because, as you can remember, we ignore the vectorial and tensorial perturbation here, and also we consider a particular election of the gauge. So we choose the Newtonian gauge, and then we write using the boundary conditions that these quantities are equal. And this quantity is known as the Newtonian potential. And the people study an effect to connect this quantity, the Newtonian potential that appears in the perturbed part of the metric, and try to connect with the temperature. And what kind of temperature is it? Is the temperature of the photons emitted from the glass scattering surface. And the people try to measure the redshift from this slice with the slice of today. I try to say they compare or try to see what is the change, what is the redshift, and connect with the temperatures. And they study the temperatures at different points in the CMB. And then, using this relation, they try to write one kind of fluctuations. Remember that this type of fluctuations corresponds to the space-time fluctuations. In this case, the quantity is the temperature and depends on the angles because we consider the spherical symmetry, and put a relation with the Newtonian potential. This effect is known as the Sachs-Wolf effect and is the mechanism to identify the observations with the theory. More or less, is clear, more or less? In that sense, we say that the theory is related, or the perturbations part. This is the term from the perturbed metric, and is connected with the structure in the sense that we can connect with the temperature. And then when the people consider, for example, the power spectrum in terms of the spectral characterization, you can read from here that you can write this expression in terms of the density, but also you can rewrite this expression in terms of the temperature, and you can connect the perturbations with the observations. In that sense, we mentioned that we have a theory which explains the data that we can observe. And let me share the presentation. Let me refresh you. In the last lecture that we studied, that was the spectral characterization, but also yesterday we study the primordial cosmic structure according to the quantum treatment. So the starting point is the same. We consider the perturbed metric with this quantity is known as the Newtonian potential, as in the other case, and then write in one equation we split the modes in terms of the zero mode responsible to the expansion and the other modes using this variable. So the perturbations on the field are considered here, and also the part which corresponds to the perturbed sector of the metric. So in one equation we have both kind of perturbations, the metric perturbations and the field perturbation. And then we try to quantize this quantity, but this quantity has information of what? Of the space-time, which is codified here, and also the elements from the field, because the perturbations of the field are written in this first term. And the people try to use the similar or the identical treatment for quantum field theory and write this variable in terms of the creation and annihilations operators. Then they choose a particular scenario in which the modes behaves as the Minkowski, as in the Minkowski space-time, and they get a solution for the Bunch-Davis vacuum, defined as Rioder's vacuum here. And this is the so-called adiabatic vacuum or Bunch-Davis vacuum. But in this case, we are working with the fluctuations on the field and fluctuations in the sector of the metric. And then the people try to reproduce the power spectrum that Harrison and Seldovich got. They use also, again, the density fluctuations. And I will mention again that these kind of fluctuations are space-time fluctuations. And then they try to get the same expression as they had in the case of the spectral characterization, but now in terms of the quantum treatment. And how did the procedure? They use the 2-point functions instead of the average that we had in the previous equation. And they consider the 2-point functions and try to extract the power spectrum from this quantity. But they try to obtain the power spectrum using the Bunch-Davis vacuum. And yesterday, we formulated a question about the kind of fluctuations that are working here. And we realized, or we recognized, that the fluctuations that appear in the functions are related with quantum fluctuations. And that kind of fluctuations are a completely different fluctuation than the statistical fluctuations, because in the case of a statistical, we considered, or the people, Harrison and Seldovich, considered an average over a big number of possible universes. In this case, we have the 2-point function, and as I mentioned yesterday, the 2-point function is related with quantum uncertainties. I mean, only the word fluctuation has the meaning of what is the uncertainty in this quantity, but the uncertainty is a completely different meaning than the statistical fluctuations. So we have the same result because they obtain the same form, the same power law for the power spectrum, but how to explain the breaking of symmetry of this state, because as we studied yesterday, is constructed with symmetry invariant on the invariant in the symmetry of this state. And also, you couldn't state how generate the structure, because to represent the structure, it's necessary to incorporate a mechanism to break the symmetry. If we started from a patch, and then we know that the universe is homogeneous in isotropic, we need a mechanism to remove that kind of notion in a proper way to generate the primordial seeds. So in this lecture, I try to explain, or first of all, try to address the questions. For example, as I showed in the previous slides, in the case of the quantum treatment, the standard version involves quantized both the perturbations of the metric and the perturbations of the field. But what could be a good approximation to describe a period after the Planck era? Because we know that dealing with quantum mechanics in GR always is really challenging. Try to work with both. So what could be a good approximation, or what are the problems we try to consider as in the example that I showed you before, which involves what? The perturbations of the metric, the perturbations of the field, and then the people quantize. The problem is not related with the perturbations, because we can consider both the perturbations of the metric, the perturbations of the field, but when the people try to quantize, how could be possible quantize one sector of the metric if we don't have a quantum theory of gravity? So in that sense, is address this first question, and then in this lecture, we try to explain how could we explain the symmetry, the breaking of symmetry of the Bunch-Davies state? Because yesterday we discussed about the collapse and the role that the collapse plays in this case, and collapse could be the responsible to breaking the Bunch-Davies symmetries. But we know from quantum mechanics that the notion of collapse involves an observer or a measurement device. And in cosmology, it's hard dealing with that kind of notions, because we know that we address the situation in the early universe. So the questions that could appear are some kind of what could be a good observer at that epoch, or what would be a measurement device to describe that situation. And it's not easy to answer that kind of questions. So we try to see how could how elaborate a new version of this problem in order to avoid this kind of questions. And then we analyze a particular problem in which the misconception of the fluctuations play part of the problem. You can see that there are differences between the different meanings of the fluctuations, but it's not only the possibility to have a problem using that kind of fluctuations or the different notions could appear in the theory, in the full model. And I'm going to discuss a particular situation or a particular problem known as eternal inflation problem. So let me start talking about semi-classical gravity. We know that it's a challenge working with a quantum theory in which GR. And despite of many efforts, we don't have a quantum theory of gravity, but we need work in some kind of scenarios, as in this scenario in inflation. We have a quantum field responsible to the expansion and to generate the structure, but also we need the part from the space-time. So what could be a good approximation or a good framework to work with both theories? Is only an approximation, because we know that put together those branches of physics is not easy. There are many works that try to get a satisfactory theory, but so far we don't have that kind of theory. But we can work with a scenario that put at the same or more or less the same level quantum and gravity scenario. And this is known as semi-classical gravity. So in the case of semi-classical gravity, the idea is that we treat the space-time in a classical way, and the other side corresponds to the matter sector, is related with the quantum version of the energy momentum tensor. So in other words, we give a classical treatment for the space-time part and give a quantum treatment for the matter. So we can see that in the previous analysis that I showed yesterday, we consider quantum. Also we quantized the sector of the perturbations. But if we remove that notion and now we move our analysis to the semi-classical gravity, we need to deal with the quantum version only in the matter sector, not in the space-time sector. So the space part remains classical, because we can think that after the Planck era, when inflation happened, the space-time behaves as classical. I know it's only an approximation. I hope in the future years we can have a quantum version of the gravity theory. Could be could be a possibility, and then we try to write the full theory in terms of that theory, if that theory exists. But so far we haven't that kind of theory, so we treat the space-time part as classical and the matter sector with a quantum behavior. So in the following, I try to show you briefly how deal with the perturbation part and with the equations that we obtained yesterday, but now in this language. So in order to address the second question is how to explain the emergence of the structure, or how to explain the breaking of symmetry of the Bunch-Davies state, or what would be a good theory or a good quantum theory to explain this phenomenon. The theory, the quantum mechanical version that we know, is capable to answer or to explain the breaking of symmetry of the Bunch-Davies state. The answer is no. The theory, as we know, is not capable to give us a satisfactory answer for this question. So let me introduce you a problem that appears in quantum mechanics, and then try to connect such problem with this scenario. So we're going to talk about quantum mechanics only for a few minutes, and let me talk about the measurement problem in quantum mechanics. There are many ways to introduce this problem or to address this problem in quantum mechanics, but I'm going to use the Penrose way to explain this. And in the standard quantum mechanics, as we know, we have two rules for the evolution. One is given by the Schrödinger equation. For instance, if we choose the Schrödinger picture, we describe the evolutions in terms of the Schrödinger equation. And this equation, we know that is a deterministic equation, and the evolution is a unitary evolution. So this process is labeled with this U, which represents the unitary evolution. And we have a different law for the evolution, and it's the R process or the reduction process. And this process is the collapse process. When the people said, when you perform a measurement on the system, or when you measure that quantity, you get a particular value, a concrete value of that quantity. But you have two kinds of evolution. One is unitary, and the second is an statistical or stochastic process, and it's related with the collapse. So the problem is that, okay, you have two evolutions, but the theory doesn't say something about when one use the unitary process or when we should use the reduction process. So at this level, we have a theory which involves two evolution process, and the theory doesn't say something about when we should use one, the first, for example, or the second. So, okay, are there questions? No. There are many, I don't know if many, but the people study how to solve this problem in quantum mechanics. How put a theory which explains the both evolutions, a theory whose postulates were clear, were transparent, to describe the evolution of a system, and also a theory capable to remove the notion of an observer or the necessity to use devices to perform measurements, because we know, or someone could argue, that at the level of the lab, the theory in terms of observers or devices, measurement devices, works, but okay, that is at the level of the lab. But if we try to describe a situation in the early universe, we don't have a lab at that time. Who could be the observer is the question that we try to avoid. So one way to solve this problem, or one theory that tries to solve this problem is the collapse model in terms of a new evolution. This is a particular class of these theories, the collapse theories, with spontaneous localization. And I try to describe what is the feature of this theory that makes different the evolution of the system. This is a theory that in one equation incorporates both types of evolutions, the unitary evolution and the reduction evolution. You can see that if I turn off this part of the equation, I obtain the standard solution for the Schrödinger equation. And let me explain what are the ingredients of this new part. This new part is related with the collapse mechanism. In this equation, the people try to write the stochastic process in terms of a noise. This noise, the people thought that the noise fills the space-time, and this kind of noise generate, and this kind of noise generates the collapse. So the collapse is generated by a noise and not by performing measurements. And this parameter codifies the collapses, how many collapses over the time we're going to have. And this is the same parameter here. And this is the usual Hermitian operator. And we're going to see that this equation or this kind of evolution represents or describes a collapse toward one or other eigenstate of this operator A. And in this case, the theory is a new theory, but in one equation, have the two evolutions. In one equation, this one equation has the two evolutions, the unitary evolution, this first term, and the reduction, evolution related with the stochastic process. So we can see from this equation that now in the evolution equation, we have the unitary component, and also we have an stochastic component in this side. And the theory says, when you don't have collapses, this term is turned off. Turn off this term, and we recover the unitary evolution. But when you have a collapse or more than one, as in this theory that we thought we have made an infinity collection of collapses, this term turns on. So in one equation, we have the two evolutions, and one ingredient that is really important here is this kind of noise, because this noise now has the responsibility to generate the collapses. With the universe is filled with this noise. This noise generates that kind of collapses. But in this point, we can see that we remove the notion of an observer or a measurement devices to collapse the state, because we thought that the collapse is regarding this noise. In this case, this calligraphic T represents a time ordering operator. And for example, in the practice, the people considered, in order to simplify the equations, that this is a white noise. And this is a random classical function on time, because the noise changes with the time. And as I mentioned, this lambda codifies how many collapses happen in a period of time. Also, we have the Born rule, and the Born rule is given by this equation. And this is a new theory, and this theory tried to solve the measurement problem. The measurement problem, because in the Copenhagen interpretation, we didn't know how to deal with these two kind of evolutions, and we wrote the theory in terms of observations or measurements process. But in this case, we remove that kind of notion because we attribute to this quantity the generation of collapses. So do you have question at this point? I know that this topic is not essential in cosmology. It's a brief comment to address in a different way the cosmological scenarios, because I want to address the primordial cosmic structure in terms of semi-classical gravity and collapse theories. And what is the point to start is the same, because we're going to consider both the perturbations on the field and the perturbations on the metric, but then we try to quantize only the matter sector, because as I mentioned, we try to describe the scenario in terms of semi-classical gravity. So I need a theory which involves a quantum treatment for the matter sector but give a classical treatment for the space-time sector. So I try to address the emergence of primordial cosmic structure in terms of semi-classical gravity and collapse theories. And we can consider the variations on the action that I showed you in the first lecture, but then we can write the action in terms of this new variable and then obtain the corresponding Hamiltonian. Why we can perform the same calculation without semi-classical gravity or collapse theories, but in this case, I try to obtain the elements that I need in this case, but I try to extract the ingredients using both equations. So I consider the perturbations on the metric and then consider the Hamiltonian, the variation on the Hamiltonian, and the semi-classical equations to the first order are right in this form. Again, from this equation, you can read that the space-time part remains classical, while the matter sector has a quantum treatment. So again, we can make a choose of the gauge, and then using corresponding approximation, and we can derive a new version from our equation that I showed you in the previous slide. Someone asked me about the relation between the Newtonian potential and the observable quantities. But in this equation, if we use the Einstein semi-classical equation and combine with the perturbations of the metric, remember that this quantity is known as the Newtonian potential. We can write in one equation the Newtonian potential and in this case, the momentum of the field. As you can see in this equation, you write the Hamiltonian in terms of the conjugate momentum, and as in many examples in classical or analytical mechanics, you can write in terms of the conjugate momentum. And in this case, we have a relation between the Newtonian potential and the conjugate momentum. But this equation taken into account the semi-classical approximation. And this result will be useful for computing the power spectrum in this case, because the people, I try to summarize, this is a larger work on how to obtain the primordial cosmic structure and obtain the power spectrum is not easy, as I put here, but I try to summarize the main ideas. Consider perturbations in the action, then obtain the Hamiltonian using the semi-classical equations, the Einstein semi-classical equations. To the first order, we can obtain this relation between the Newtonian potential and the conjugate momentum. And also, if you try to connect, you can connect this quantity with the temperature, and then you obtain a relation between the temperature and the conjugate momentum. So this is a new way to read the observations. And they obtain a power spectrum and try to see what happened when, in this case, this K, again, is a quantum treatment for the matter. So this K represents the modes of the field. And when I turn off this part, I obtain this part. but in the case that we don't have collapse, this is equal to 0, and also for this term. So we have an equation in which we write the power spectrum. Remember that the power spectrum, in this case, we have an average. And you can ask me, oh, but why is the reason? Because now you're considering this bracket and also the line that represents the average. Because in this case, I try to compute this quantity, these 2-point functions in terms of the state, but the state, the rule for this state is right in terms of collapse theories. And now, using collapse theories, you have a unitary part, but also we have a stochastical part. And this part we mentioned that is related with collapse. So in other words, collapse generates the breaking of symmetry because incorporate an stochastical term. And yes, thank you for the question. It's a really good question because, sorry, I haven't mentioned that in this case, I use A to represent a generic operator, but this theory has one of the degrees of freedom of this theory is the election of this operator. You can choose this operator, for example, as the field operator or a position operator or the momentum operator. So in this case, I use these people use the field to represent the operator, which offer the collapse. And thank you again for the question, because I had to clarify this part. It's really important to clarify that 1 degree of freedom of this theory is the election of the operator, which offers the collapse. And the operator could be the field, the momentum. In this particular case, I show you the case in which the momentum, sorry, the field collapses. But in this work that I put the references later, but the people use also the momentum to get the spectrum, and they obtained a different spectrum, but the spectrums are scale invariant. In this case, we can see that if we turn off the collapse, we turn off this power spectrum. No, thanks for the question. And if we try to explain the emergence of a structure, we need to incorporate the collapse, because this lambda represents how many collapses happen in one period of time. But if we turn off this term, and if we consider that we don't have collapses, this part of the equation doesn't play a role, and we only have the unitary term, and we don't have a structure. So to explain the structure, it's necessary to incorporate the terms which involve the collapse. So this is one result that, sorry, I forgot to put the reference here, appear the reference, but in the next slides, in the following slides, but I put the reference here, sorry. But these people try to address the explanation of primordial cosmic structure in a framework which involves work with semi-classical gravity and with collapse theory. So they try to explain one of the questions that we addressed before. So how to explain the breaking of symmetry of the Bunch-Davis state? And now, using this equation, we can give a good explanation for that kind of breaking of symmetry, because at this point now we found an element to represent the breaking of symmetry in terms of collapse. So, do you have any question at this point? Are you, okay. What do you think about this quantity? This quantity is responsible for the generation of collapses, but one question could be, for example, now you remove the notion of observers or a measurement device, but from where came these terms? And it's an open question. It's still an open question, and for example, in terms of the Penrose theory, he tried to describe this kind of noise in terms of quantities related with the space-time geometry. But so far, we don't have a theory which explains the emergence of this kind of noise, but it's an open question, and since my point of view, it's an interesting question, because in this point, we remove the notion of observers, of measurement devices. It's really good following to this point, but there remains different questions, and we try to solve that. We are talking about the collapse of what quantity? The wave function, okay. We try to collapse the state. In this case, it describes the collapse towards one or other eigenstate of the operator of your election. As I mentioned before, this 1 degree of freedom in this theory is the election of this operator. So the theory describes the collapse toward one state of this operator, one or other state from this operator, with a collapse rate labeled here. So the theory, or try to collapse the toward one of the states of this election that you performed before. So, for example, I write only the cat, and maybe it was not the best idea. But if we try to compute this bracket or these 2-point functions in terms of the Bunch-Davis vacuum, before, when we address the theory in terms of the quantum version without collapse theories, we only have the unitary part in the evolution rule. So to incorporate the breaking of symmetry, in that case, we had to evoke the collapse process. But in that theory, the collapse process is wrought in terms of the notion of an observer. In this case, we remove that kind of notions and we incorporate these terms. And when we try to compute the power spectrum using the Bunch-Davis state, the state in that case is not in that case. In general, the Bunch-Davis state is homogeneous and isotropic, and we have now a mechanism to break that symmetry on the state. So when we compute the 2-point functions in the Bunch-Davis state, now we have a mechanism to break that symmetry, because this mechanism tries to collapse to one eigenstate, to the operator. And in that sense, we have an element to break the symmetry. I don't know if I answered your question. Let me know, please. Okay. So I explained briefly how to incorporate a semi-classical framework. The semi-classical part contribute using this equation, because this equation allows us to use the connection between the observations and the perturbations of the metric. So we have a relation between the conjugate momentum, the Newtonian potential, and the temperatures. And the people try to read in that way the the data from the CMB, and as you can imagine, the predictions changes with the standard predictions if you use this theory. In what sense the predictions are changing? In the sense that that you are considering, for instance, the tensorial modes. I only represent here the scalar perturbations, but in this theory, as I tried to illustrate yesterday, we can have tensorial modes. And when we address the theory in terms of semi-classical gravity, even without collapses, if I write the theory in terms of semi-classical gravity, the predictions for the tensorial modes change. And the predictions for the primordial gravitational waves are changed. So I mention only that features, because from this equation comes only from the semi-classical gravity scenario. It holds even without collapse theories, but this equation give us the different notions or the different predictions for the power spectrum. So then we have an answer. Is not the final answer, is not the only one possibility, but is one explanation for the primordial cosmic structure. How to explain the breaking of symmetry? We can explain the breaking of symmetry using collapse theories, because collapse theories incorporate a mechanism which involves an stochastical part. And you can imagine that, you can realize that when you have this equation, in this left side of the equation, I use a bad notation because I put the notation that the people who developed this theory used, but I could write this equation as I showed yesterday in terms of the 2-point functions. And in that case, the people talk about the quantum fluctuations, but in that case, in the case that we studied yesterday, we refer to quantum fluctuations in order to describe an uncertainty, or we use the word quantum fluctuations to represent the uncertainty in one quantity, because evolution was wrought in terms only the unitary part. But now you can see from this equation that we have both evolutions. We have the unitary evolution and the stochastic evolution. So when we perform the 2-point functions or when we try to study the quantum fluctuations, instead of have uncertainties only, we have statistical fluctuations, because this random variable incorporate to the theory a random process vinculated with the stochastic behavior. So at this point, we have a mechanism to introduce the element which missed yesterday, that lag in the last scenario. So at this point, we have answer in the sense that it's not the final answer. It's only a way to solve these problems, but many people try to deal with these kind of problems, and there are other ways in which they address the problem, and then they have a different solutions. But in this case, we try to give a good approximation to describe the inflation period, which is a period after the Planck era, and the answer is in terms of semi-classical gravity. Semi-classical gravity is a good approximation to describe an era after the Planck epoch, and using a quantum field, but work with a classical scenario. I mean, we still working with the Friedman-Lemaitre-Robertson-Walker metric, but instead of quantize the perturbations of the metric and the perturbations of the field, with semi-classical gravity, we only quantize the perturbations of the matter. I mean, the perturbations of the inflaton field. And then how we explain the symmetry breaking of the Bunch-Davis state, we introduce a new version of quantum theory. That kind of theory emerges from or in order to solve the measurement problem in quantum mechanics, and this theory is capable to explain the breaking of symmetry of the Bunch-Davis state. So the people reproduce the power spectrum using this theory and address the scenario in terms of semi-classical gravity. But now let me show you, because someone could answer, and also I'll put the reference at the end. I'm sure that I wrote the reference at the end in the last part. But the form for this power spectrum, again, have the same power law as in the previous, in the spectral characterization or in the quantum treatment without semi-classical gravity and collapse theory. So in that sense, the people who developed this analysis claim that the theory is explained in terms of semi-classical gravity and collapse theories. But let me illustrate now what could be a problem related with the misconception of the quantum fluctuations in the standard cosmology. So I try to describe an open problem in the cosmology community, which is known as the eternal inflation problem. Because many of the authors or developers of the inflation theory now moves to other theories because they claim that the theory has a problem known as eternal inflation problem. So let me introduce what is the eternal inflation problem, what we understood in the standard version, and then we try to analyze with the elements that I showed you previously. And let me explain again. First, or before to explain the eternal inflation problem, I summarize one thing that we study in the second lecture. We mentioned that the inflation period has many advantages. Among them, the explanation for the natural or the inflation period is capable to solve naturalness problem as the horizon problem, but also the emergence of a structure. So in this lecture, or in this whole lecture, this class, we try to study both characteristics, the expansion and the generation of the structure. Let me see if this, okay. Can you see my, no, I think you can. Sorry, early universe to session. We explain the inflation mechanism in terms of the slow roll mechanism. So we took an action. In this action, we have this potential, and this potential codifies an effective constant, cosmological constant, because we try to represent a mechanism to explain the inflation and the expansion in the beginning of this epoch. We have a biggest potential, and then over the time this potential decreases to zero. In this case, we use the assumption that to explain the expansion, we only use this mode. And as you can see, this mode, the zero mode of the inflation field, depends only on time, not on the position. And we describe the mechanism using the Einstein and the Klein-Gordon equations. In these equations, we take the approximations. What are the approximations? Are that this cosmological constant is bigger than the kinetical term. So we vanish this part and we obtain a relation between this H and this cosmological constant. And also we consider that we thought in the situations in which we thought the zero mode of the inflation field has the behavior of a classical particle. This is only an analogy that the people use to describe the slow roll mechanism, because the people thought, had the idea that this zero mode of the inflation field rolling on the potential toward the minimum, and in slow roll over the potential over a characteristic time, and the people thought that the inflation behaves like a particle which suffering the terminal velocity, and the terminal velocity, as in other examples in physics, is right in this form, and we wrote this equation in terms of the conformal time, and we obtain this equation, and then obtain the equation which describe the velocity, and an equation to describe the classical displacement of the zero mode of the inflation field. And this classical displacement represents what is the displacement that the zero mode of the inflation field obtained rolling down the potential over a characteristic time. So this is the mechanism to explain the accelerated period in the early universe, and then how to turn off this period. Then so what is the eternal inflation problem? The people then thought the following idea. Okay, we know that the field, sorry, because I had put the level of 0 because I tried to describe the zero mode of the inflation field, but I use the notation that the author used in the paper. So the people thought the field is rolling slowly over the potential that you choose. In our case, for instance, the harmonic oscillator potential. And over a characteristic time, we mentioned that one possibility for this characteristic time could be the Hubble time. And over this time, the field has a classical displacement, the classical displacement that we obtain from the approximations in the Einstein equations. But the people argue that this field, as other fields, when the people treat quantum, has quantum fluctuations, or the field suffer quantum fluctuations. But the people thought the quantum fluctuations in terms of this form. We know that the uncertainties are related with this quantity because we studied previously the differences and the meanings of this kind of fluctuations. And the people mentioned, I described the standard version. The standard version name quantum fluctuations for this quantity, and this quantity appears in the slow roll mechanism. And then if we have but the classical displacement and the quantum fluctuations, we have two possibilities, because the people thought, yes, I have the picture here. The people thought that this is the effective cosmological constant. This is the zero mode of the inflation field, which rolls down this potential. And this particle rolls down the minimum towards the minimum. And we have the classical displacement, which comes from the Einstein equations. But the people have in mind that quantum fluctuations is something that generate jumps in the zero mode of the inflation field. Again, I'm describing the generic or the standard version. Is not the version according with the definitions that we study. But let me show you first the standard part. So they thought the quantum fluctuations as jumps in this particle or in this zero mode of the inflation field. And they thought that quantum fluctuations could make that this field backs over this potential. And then they have the two possibilities. The possibilities in which the classical displacement dominates, so comparing with the quantum displacement, and the other possibility in which the quantum field dominates over the classical displacement. So the people thought we could have the possibility in which the classical displacement is bigger than the quantum fluctuations, and the inflations are known here, and the story of the universe as we know continue in a good sense. But also, we could have now we introduce a new possibility in which the quantum fluctuations dominate. And if quantum fluctuations dominate, we have the possibility that this zero mode of the inflation field goes back over this potential, and then the effective cosmological constant again were bigger than in other points. For example, if I thought in this part, we have a effective cosmological constant at this level, and this is not bigger as when the inflation period started. But if the quantum fluctuations achieve that this zero mode of the inflation field backs on this over this potential, the effective cosmological constant again is bigger. So in that sense, we have two possibilities. But for example, from the 11 equation, we don't have a problem, because in that case, we reproduce the standard history and the history according to the observations, and we don't have a problem. But what happened if we have the case in which the quantum fluctuations dominate over the classical fluctuations, over the classical displacement? In that case, again, we have two possibilities, because the field will move up in one case, but also in other case could move down the potential. So we have two possibilities. But what happened in the regions in which the field moves upwards, as I showed you previously? If the quantum fluctuations made the field moves backwards, we will going to have a biggest value for this effective cosmological constant, and the rate of the cosmological expansion will be increased. But for other thinking in the other case, in the regions in where the field went down, we don't have a problem, because the regions going to have an expansion not biggest as in the first case. But what's going to happen when the time passes, when we consider the situation in a period of time, the regions in which where the field went up grow more, because they have a biggest rate of cosmological expansion. And when we compare with the regions in which the field were down, the regions that predominate in the scenario going to be the regions in which the field went up, because that regions has a cosmological expansion bigger compared with the others. So in that sense, the people thought that the zero mode of the inflation field responsible for the generation of the structure and generation of the expansions backs, according to the quantum fluctuations, backs on the potential and still have a cosmological constant. So this is not according with the observation and not with the story that we know on the cosmological model. So the people in that sense thought that the inflation never ends because the quantum fluctuations holds the zero mode of the inflation field in one region before to reach the minimum. So the effective cosmological constant never turn off, and then the inflation never ends. But this is the standard version to address this problem. I don't know if you have questions in the chat, but let me read. Eternal inflation is so worrying in any field. We heard it. I don't understand the question. What do you have in mind when you mention any field? In this case, eternal inflation appears, maybe could appear in other problems, but here we have this problem, sorry, because we have on mind the idea that in the action we incorporate, no, this is not. This term, let me show you. 3, 4. No. Sorry. In the 2 lecture, in the 3 lecture. No, this is the first lecture. Sorry, let me show you. Yes, I have. In the action, we introduce this potential to describe an effective cosmological constant. So this field represents the matter sector, and this potential represents the cosmological constant. So we obtain the equations, the dynamical equations for the zero mode of the inflation field. They take the assumptions that the zero mode of the inflation field behaves as a particle and a slow roll along this potential. And this particle behaves like a particle reaching the terminal velocity. So in that sense, we obtain, or with that kind of assumptions, we obtain the classical displacement for the field. And then we obtain an equation to describe in terms of the expansion and the cosmological constant, but we have in mind the idea that this is an effective cosmological constant in the sense that at the end of the inflation period, this must be turned off. So in the problem that I try to illustrate here, the people have in mind that this effective cosmological constant never turn off because the quantum fluctuations could generate jumps on the zero mode of the inflation field, and they thought that this kind of jumps makes that the zero mode of the inflation field moves upward the potential and downward the potential. But in the case in which the zero mode of the inflation field moves in the up direction, we have the possibility, or we recover a cosmological constant with a bigger value as in the beginning of the inflation. So instead of have the situation in which the zero mode of the inflation field rolls down to reach the minimum of the potential, we have a situation in which the zero mode of the inflation field suffer quantum fluctuations, have the possibility to move upwards, and in that case, you have a cosmological constant that never turned off. So also you have regions in the spacetime in which the expansion rate is bigger compared with the region in which the field moves down the potential. So over the time, you're going to have the situation in which the regions that are going to predominate are the regions in which you have a biggest cosmological expansion. So this cosmological constant remains turned on, and never the inflation period never ends. And in that sense, you still in this part. I don't know, maybe you could have the same problem if you use, for example, a different potential, or if you use a different mechanism to explain the expansion. Many people use, for example, not only one scalar field, they could use more than one, and the problem persists in that kind of scenarios. So I don't know if the question is in that sense, but the problem is still remains in all the models of the inflation. Of the inflation description, but as this could work not only for the eternal inflation problem. In every time that we read about one problem, first of all, we can ask, okay, but this is a real problem, or is a well-posed problem? And in this case, I present to you the objections to describe this problem in terms of these words. So the first objection to describe this effect as a problem is the distinction between fluctuations, because we mentioned in the previous lectures that quantum fluctuations represents only the indeterminacies of some quantities and are not related with statistical fluctuation. So in that case, the people, when thought the quantum fluctuations as statistical fluctuations, had a misconception, because the idea that they had in mind is that the quantum fluctuations behaves as statistical fluctuations. But if they work with the standard theory, they don't have any worry, or they shouldn't have any worry about that situation, because they consider only the unitary evolution. If they try to use the statistical part, they have problems, because they have a theory that write the statistical evolution in, or the stochastical term, in terms of a collapse, and collapse is related with an observer or a measurement device. So in that case, it's a misconception use quantum fluctuations as statistical fluctuations. So if you recognize that quantum fluctuations, the meaning of quantum fluctuations is the uncertainties and over the quantities, you don't have the problem, because quantum fluctuations only represent the weight of the wave function, for example, and not the case in which you have an statistical fluctuation. So in that sense, you don't have problems. And also other argument could be that we use the zero mode of the inflation field to generate the accelerated expansion. And as I showed you before, the zero mode of the inflation field is position independent. So if the zero mode of the inflation field is position independent, it's because represent an homogeneous and isotropic behavior. So we don't expect that the things changing from one point to the other, because the symmetry of the zero mode of the inflation field. So we have two ways to claim that the eternal inflation problem is not a really real problem. But again, if we treat the fluctuations only as quantum fluctuation, as in the case in which yesterday I showed you that in the 2-point functions, we only refer to the uncertainties of some quantities and not in statistical fluctuations. But you can tell me, okay, but in that case, you don't have a mechanism to generate the structure because you don't have the element to break the symmetry of the Bunch-Davies state. So you need to incorporate the statistical fluctuations in your theory to give a satisfactory version for the structure. But if you thought that, or if now you incorporate the statistical fluctuations in your theory, as in the theory that I showed you previously, using in this version of the theory, we incorporate a mechanism responsible to generate statistical fluctuations, not only indeterminacy. So now you have a theory which incorporate statistical fluctuations, and you have again the possibility to have this problem, because if you incorporate statistical fluctuations in your model, is good, because now you have an element to give account for the primordial cosmic structure, but you recover the possibility to have eternal inflation problem, because now at this point, you have a mechanism who represents this situation. In the same situation, but right in terms of statistical fluctuations. And now we have the possibility to have this problem. But one part or one project that I study in my PhD is try to see if the eternal inflation problem have a solution using semi-classical gravity and collapse theories. And I present to you in the last 10 minutes of this session, but I want to know if you have questions at this point. Okay. I know that in this lecture, I presented many topics, because let me, before show you the solution of that problem, let me summarize the things that we studied. The questions that we had in the previous lecture, or at the end of the previous lecture, were what could be a good scenario to describe the inflation period, which is a period after the Planck era, and we want to deal with a quantum field. So the answer is, or one of the possibilities to describe this problem, is the scenario of semi-classical gravity. Is the scenario in which we treat the matter sector with a quantum behavior, and the classical spacetime, and remains classical the spacetime, the behavior of the spacetime. And then the second question was, how do we explain the symmetry breaking of the Bunch-Davies state without the notion of an observer or a measurement device? And here we try to answer this question using collapse theories. Using collapse theories, we have now an element to incorporate the stochastic part in the evolution equation, and this stochastic part represent or give account for the breaking of symmetry of the Bunch-Davies state, and generate and explain the generation of the primordial cosmic seeds of the structure. And the last question is, what are the problems that cosmology attempts for treating fluctuations incorrectly, or for have a misconception on the meaning of fluctuations. One problem is the eternal inflation problem, because we recognize, or we see that if we recognize that quantum fluctuations represents uncertainties, we don't have this problem. But in order to give a satisfactory theory for the primordial cosmic structure, we need to incorporate collapse theories. And in that case, we incorporate a statistical fluctuation. So the price to pay to use the framework of collapse theories is that appears again the possibility to have eternal inflation problem. And now let me show you that in this is the reference, sorry for right at this point, but this is the reference which introduce the study of the primordial cosmic structure in terms of the semi-classical gravity and collapse theories. And I wrote in this part that the authors examine the two cases in which the momentum operator collapses and then when the field itself collapses. But we study the case in which the field collapses, and we have a form for the power spectrum. Is the form that I showed you in the previous slides. And I talk about one degree of freedom in this theory, and is the election of the collapse operator. But we have a second degree of freedom in this theory, and is give a form for the noise, and that implies that we can have a form for the collapse rate. And the people choose a particular form for the collapse rate in order to have a scaling variant power spectrum. So they use this result. This result represents how many collapses we have in a period of time, and in this case is related with this K. This K is vinculated with the mode of the field, and we try to see what are the modes that could generate a problem of eternal inflation. So we study, we know that the mode that is responsible for the expansion is the zero mode of the inflation field. And in the case for the zero mode of the inflation field, we don't have problem, because if this mode is equal to 0, we have a collapse rate equal to 0, and we don't have a problem. But what could happen with the modes that have a large wavelength, almost to the zero mode of the inflation field, and behaves effectively like a zero mode of the inflation field. So we try to characterize what kind of modes could generate eternal inflation, and we choose the modes that are bigger than the particle horizon this quantity is the quantity that we study in the first lecture, and we study that a particle horizon codifies the causal connection between regions. So for that reason, we choose the modes bigger than the particle horizon to study the modes that could affect in this scenario. And the physical wavelength is right in terms of the scale factor. And also in this case it's different. In this case we try to represent the wave number, and this is not the lambda that represents the collapse rate. In this case, this lambda represents the wavelength of the modes that could generate eternal inflation. And we focus in a period in the inflationary regime. So instead of focusing only in the zero mode of the inflation field, we talk in the modes that have a behavior similar to the zero mode of the inflation field, and we use the particle horizon to separate that kind of modes could affect in this case, because the particle horizon gives us a notion of causal connection between regions. So we study this part, and then try to put a bound to sum the most that could affect. I only use the result. This is the statistical uncertainty, because as you saw in the previous slides, the evolution is right in terms of a statistical term, and we study the statistical fluctuations. If we take a synonymous here, quantum and statistical fluctuations is valid because the theory that I presented work with both stochastical fluctuations and quantum fluctuations. So in that sense, in this case, could be no exception, talk about the quantum fluctuations, but of as statistical fluctuations. So we try to compare both quantities, the classical displacement compared with the quantum displacement or the quantum fluctuation, and try to see in which, if we have a solution, or if we have the case in which the classical displacement dominates over the quantum fluctuation. And we study that situations using a bound, for the wavelength. We perform this integral and we obtain what is the quantum fluctuations. What are the, let me skip this part. It's only a brief comment about the collapse rate. Using a particular source of the collapse rate, we can perform the integral, and we choose the parameters for case in order to get a consistency with the CMB data. And we compare this quantity, and we found that this inequality, if this inequality holds, we have a solution. If we find a solution for the parameters alpha and beta, we have a solution for the problem. And we try to see if there exists one region in which we have a solution for alpha and beta, such that this quantity is less than 1, and we find that in this region we have a solution for eternal inflation problem. So I try to illustrate that if we consider in a bad sense the notions of quantum fluctuations, we could have a problem in the sense that we don't have a well pose of the problem. And we have the idea that our theory could be bad, but if we try to work in a clearly way, using it's not easy dealing with the stochastical terms here, but it's a theory that could give you a good explanation to generate the structure. And also, at the first glance, seems that we have we recover the problem of eternal inflation, but no, if we study, we detail the problem and we try to see what happened, we realize that we don't have a problem, or we have a region of solution for this problem. So maybe I try to give you the mainly conclusions for this whole period of lectures. And we know that inflationary period in the early universe is capable to solve some kind of problem as the naturalness problems, and also generates a structure. The inflationary period, or the biggest successful of the inflationary period, is the capability to give a satisfactory theory for the primordial cosmic structure. And the people say that argument because they recover the power spectrum in terms of the primordial power spectrum with the same form as the horizontal Dawich spectrum. But if we analyze carefully the conceptual part of the of the problem, we realized that there were many questions open, as the question regarding who is the observer in the early universe, or what is the element responsible to breaking the symmetry. And also we discovered that in the literature, not in all references that I wrote, but in many of them appears the misconception between the fluctuations. So it's really important to distinguish between the notions of fluctuations. Every time that you read, for example, quantum fluctuations generate this problem, try to understand what is the real meaning of the word, because could be the possibility that they use the word quantum fluctuations, but they try to but they use the as synonymous of statistical fluctuations, and it's not valid in all the scenarios. In this case, it's valid because I work with a theory that have the two elements, the unitary evolution and the stochastic evolution in one equation. But if you have the standard theory, you only have the quantum fluctuation, which the meaning is the uncertainties. If you try to write the statistical fluctuation in that case, you attempt the questions of what is who is the observer at this point, what is the tool device that you use the measurement device that you use to describe the measurement at that level, to incorporate the collapse. So in order to avoid that kind of question, we address the problem in terms of collapse theories and in terms of semi-classical gravity to give a description in a period after the Planck era, but dealing with a quantum field. So the lesson to learn here is in the cosmological literature, or not only in the cosmological literature, in many branches of physics, which fluctuations are involved, we need to be carefully with the meaning, and we try to think in the problems. If you read about one problem, first of all, try to see if the problem is well posed. If the problem is not well posed, try to figure out what is the reason, because you don't have a well-posed problem, and try to be carefully with the meanings of the words and try to describe. Now we know that the inflationary period is a satisfactory period in order to solve many problems, in order to generate the structure, but it's not the final theory. Still many problems with this period, but this was a briefly lesson of the early universe. So please ask me many questions, not only for this lecture, for the whole week. You can ask me.
Well, while people are taking the time to ask questions, let me first of all thank you, Rosa Laura, for this lovely presentation, the entire course. Let me emphasize that one of the goals of the school was to help bridge the gap between the syllabus of a standard general relativity course that it's widely available as in the undergrad level, and current research topics, and you did exactly that. So thank you very much, and I think on behalf of the students, I can thank you for that. But for everyone in the room, now is your chance. Ask Rosa Laura questions about anything in the course, or you can even ask general ideas
Yes,
or anything.
Yes, or cosmology questions in general. Maybe I'm not an expert as other people, but I try to address the question, or try to solve the question, or talk about references. So please ask questions. I thought this last part of the lecture was dense, in the sense that I dealing with the quantum part and the classical and the GR part always is it's not easy, as you can see, but I can try to answer your questions. I don't know if the questions that I try to answer in the middle of the lecture was answered in a proper way, so please let me know if you agree with the final answer.
Hey, this is your last chance. Ask question now.
It's your last chance.
Okay. Apparently people are quiet or shy, but let me, on behalf of the organizers and of the students, thank you once again for the lovely course, and I hope you all enjoyed. So I'll
Thank
stop
you
the
so
recording.
much
Yeah.
for the opportunity. Thank you so much for the
Perfect.
whole event. I think it's really useful for us as
Yeah,
as lecturers and for you.
hopefully
Uh,
people found it useful, and perhaps people from the future are watching us on YouTube eventually as well.
yes, someone asked in the chat, but I think there are questions in direct message.
Okay, anything you want to share publicly before I stop
But
the
I
recording?
can read the question without the the name I thought.
Yeah, okay. So I was just wondering if you wanted me to stop the recording or keep
Oh
it recorded.
yes, go ahead.
Do we stop the recording or do you keep it recording?
As you
Okay, so let me keep
I
recording.
think
Yeah,
it's good. For
yeah,
me,
go.
do you think that the observed deviance from the standard cosmology of the universe can be explained by perturbations or other methodologies? Let me know if I understood the question in a good manner. Well, do you think that the observed deviance from the standard cosmology of the universe can be explained by perturbation or other methodologies? Okay, the people study the space-time fluctuations, for instance, of the density in the CMB, and try to connect with the perturbation of the metric. So in that sense, the standard cosmology works very well because the theory is according, or the observations are according with the theory. So we say that the theory is a satisfactory theory in the sense that the connection with the observations can be written in a natural form. So in that sense, the answer is yes. The observed spectrum is related with the theory only in that case. But if we try to understand the delicate part, or analyze, for example, the questions about the quantum nature of the field and the other questions beyond only the observations, we need a theory more robust. So in that sense, we are happy in the sense that the observations are according with the theory, but if we still working in that way, for example, problem as the eternal inflation problem could seems a big problem in the scenario and lead a problem of multiverse, and the people argue many kind of things. But first of all, if we try to address the problem with a careful method, as distinguished, for example, between the quantum fluctuations and statistical fluctuations, and realize what could be a real problem and not a real problem, we can get a different results. For example, in the case of address the the inflation period using semi-classical gravity, we have different predictions for the gravitational waves. But so far, never the gravitational wave haven't detected. So in that case, for us, is good in the sense that it's according with our theory. But other people could argue that is the lack of the precision in the tools could be a different answer. For, I don't know if I understood the question in a good form.
Okay, so we are calling it a course. So thank you everyone for attending. Goodbye.
Wow.